All right. Okay, so here we have, so I'm going to draw a tiny little picture because we have this character table here. And so this is my molecule, okay? And I'm drawing the open circle for an arrow coming up, okay? I don't have to put the dot in there. This is it, okay? And so then I do a rotation here, and so then it's at this end down here, and it's times a +1, and so it's still an open circle, right? I've rotated it down around the C2, which is the center of mass.
Are you doing the AU line?
I'm doing the AU line. Okay, and then I do an inversion, and it would be an X, okay, but because I have this -1 here, so I have -1 times this little X, which is the fletchings on the arrow, I end up with an open dot, okay, and then the sigma H would make it, again, horizontal reflection would take the arrow coming out of the board and make it go into the board. And so I would get an X, but then I have a -1 on AU, which brings it back out of the board. And so that would be up in this end here. And so again, 2 up here, 2 down there, they don't cancel out or anything. And so I end up with this picture here, like that. And that's what's shown. Whoa. Never mind. That is what is shown down here. This one right here. Mm-hmm. So that's how you get AU out of that one. If you go on any of the other rows for that particular arrow picture, they're going to all cancel out. You're going to have a dot and an X and a dot and an X on each of those things with the 4 columns. Okay. Now, this is what quote we got using the projection operator. And so I went into Gaussian and calculated all of those, and here they are, and they're solid. They're exactly what you got out of Gaussian. I don't know, did anybody else do Gaussian calculations to check your work?
I did.
You did? Okay. Yeah, so you can go into Gaussian and do a frequency calculation, and this is the one with see the little tip of the arrow here? I can't draw, but that's the tip of the arrow coming out of those 2 hydrogens. Okay, and then here's the OO stretch. So the oxygen stretching, so those other bonds don't change, the angles don't change. Here, zoom in, here's the asymmetric bend, here's the symmetric bend. Okay, and then here's the symmetric stretch. And this is the asymmetric stretch. The reason I drew this with a stick, just a line formula instead of a ball and stick, is because there was a big old ball here, there was a bond there, and a big old ball there, and you couldn't see that arrow. And so in order to show the shrinking bond, because they draw the arrows right on the atoms that are moving, not to the side like we do, you couldn't see that arrow. And you just saw one arrow coming out of the other bond, and that wasn't an accurate picture. So those are the 4 modes. Notice how Gaussian also got the symmetry correct, because it's using the projection operator too. Okay. Okay, so these are all of the arrow diagrams, and we got all of them right. Okay. Now, one thing that I would like for you to be able to do, though, is also see this Cartesian symmetry row. Okay. So let's do this one. It was the easiest one. These arrows are both pointing out of the plane of the paper, and that's the z-axis. Yeah, so that's not a problem. In fact, I'm not capturing this. Let me go back to display capture. That way people can see what I'm talking about. Okay. Yeah, so these arrows are coming out of the z-axis, or coming along the z-axis, and so they're going to have z-symmetry. So you should be able to look at that arrow diagram and label the Cartesian symmetry as well. This one, if you're standing on the origin and you look to the right, you see those arrows are both going in the right in the x direction and a little bit in the y direction, and so that's x symmetry and y symmetry, but mostly x. This one's strange. This hydrogen's moving to the right around the center of mass, and this one's moving to the left around the center of mass. The oxygens, I put those arrows on there just to show that the molecule's not rotating. But it has the same symmetry as RZ. So if you can look at those arrow diagrams and say, this is rotational, looks like rotational symmetry, I know it's a vibration. It's not rotation. But it has the same motion as a rotation. It's just being stopped because the other atoms are going the opposite direction. Okay, so it's doing this. See, it's rotating around the z-axis. It's not rotating, but it looks like it's trying to. And it has the same symmetry as rotation. And so for Cartesian symmetry, if you were to go up here, you could say that has RZ symmetry, therefore it's AG. So it's another way for you to assign the Milliken notation to these. If you recognize, and you don't want to go through the projection operator, if you recognize that it has Z symmetry, then it's AU. If you recognize that it has RZ symmetry, then it's AG. And so you can use those Cartesian symmetries. Now if we stand on the x-axis here, on the origin here, and we see the oxygens moving away in the x and minus x direction, those arrows are sort of increasing in both directions. That would be x squared. If they were both going in the same direction towards positive x, that would be x. But since they're you can think of those arrows as sort of increasing motion. If they're increasing motion in both positive and negative x, then it's like a x squared signal. So it would be x squared or AG. Here, these arrows, again, one's coming towards the origin, one's going away from the origin. And so they're going in the x direction and the y direction. So there'd be x and y symmetry. In this particular character table, those are on the same row, so that's fine. And then here, they're both moving away from the origin in the x direction and the y direction. So that would be sort of an x squared signal and a y squared signal. You come up here and find x squared and y squared. Those are on the top row, and so those are AG. So this is kind of using that Milliken flowchart that I had, how to decide whether, the Milliken notation using that flowchart. Okay, all right. Now let's look at the MO part. So then draw the SALCs for H and O and labeling them with their symmetries. Combine the SALCs to create an estimated MO diagram for hydrogen peroxide, and then place those valence electrons into the molecular orbitals and label the HOMO and the LUMO. Okay, so this took me forever. Trying to draw it with the drawing program. I did it pretty quickly by hand, okay, but that doesn't look very nice, and then certainly not YouTube quality, right? So I was sitting in Starbucks for I don't know how many hours, 2 hours at least, drawing these little things in CHEM Sketch. So if you want a free drawing program, this whole MO diagram was made with CHEM Sketch. So you can Google ACD Labs, ACD, all caps, ACD space LABS, Labs. And CHEM Sketch is the product that you want. It's free for educational use. And you can download it, install it. It's great. You have to sign up for their little, you have to give them your name and email, and then they'll email you the link. Okay, but I haven't gotten any spam from them that I can tell. So it's not like you're signing up for something that's going to spam your inbox. And then they have different templates. So they had a little orbitals template, so I could get p orbitals and put those in there and make some cute little pictures. So on the left, we have the hydrogen SALC AOs. And so you have the BU combination and the AG combination. So y'all should have gotten that pretty easily. So y'all have those two combinations, yes? So the hydrogens are pretty easy. Let's go over to the two oxygens. This is essentially the MO diagram for O2 over on the right. So let me scroll out a little bit. So down at the bottom, we have the two 2s orbitals. And then we have the 2s orbitals out of phase with each other, the BU combination. And then we have the two p orbitals. In this case, it's the px orbitals. The pz orbitals are the AU combination. The py orbitals here are BU. And then we have this one, which is xy, x times y. So that combination of plus minus in the xy plane is x times y. And so you just go to the character table and find that x times y, and that's the AG row. This one is plus minus, but it's in the xz plane. And so that's xz. So you go and you find xz in the character table, and then that's BG. So yeah, you can use the projection operator to get these, but you can also know that if I have p orbitals that are in phase, I'm going to have p orbitals that are out of phase. And I'll swap the shading on one of them, and then I can just use that pattern to figure out what symmetry it is. And then this top one is the x orbitals, the px orbitals out of phase with each other, and they have x symmetry. So are there any questions about the O2 side, the symmetry adapted linear combinations? This should be a review on the O2 side, a little bit of review from your undergrad, where you had the basically diatomic molecular orbital diagrams. And so now we then combine those things with same symmetry. So the AGs will combine and the BUs will combine. And then there was nothing on the hydrogen side that had BG symmetry and nothing that had AU symmetry. So those come across unchanged. Okay. So the bottom ones are straightforward. So the AG, with this AG in phase with the two s orbitals, you're going to get that lowest energy orbital MO with no nodes. Makes sense, no problem, okay. And then this one is the BU, so let's go ahead and mix in the hydrogen BU, come down here, and we make this one with one node. Then we have the AG with the PX orbitals, mixing in with the hydrogens, AG, and that, again, pretty straightforward. The hydrogens are the same color as the outer parts of that that combination of px orbitals. And then let's go up here to the antibonding version of that. So we have this BU where these are out of phase with each other, and then they're in phase with these two hydrogens. And so the outer part of that orbital is compatible with this hydrogen, and the outer part of that one is compatible with that hydrogen. So those are all of the ones that are sort of end-on or sigma-type interactions. Then we get into the pi-type interactions, side-on interactions. So BU, this one here is obviously compatible with this BU because of the shading. And so that one didn't increase any nodes, and it gave the electron more freedom or more size to roam around in, and so it's lower in energy, so that would drop in energy. This one up here, they're out of phase with that orbital. We get a couple more nodes. So we have a node here and a node there. And some of these are going to be really kind of hard to draw the nodes in some of these. Then we have the AG, what looks like sort of an anti-bonding arrangement in the oxygen 2pYs. But they're in phase with this AG motion of the hydrogens. And so we still just have one node, more freedom, so it drops a little bit, somewhat in between those two orbitals. And then we have the antibonding version of that, where it's out of phase with those hydrogens. And what else have we? This one, I guess we haven't covered.
Yeah, when I was looking at the Gaussian file that showed the things, I could not get that one to make sense.
Okay.
I was trying to figure it out.
Yeah.
I was like, I know it should be something like this, but...
And so then, this AU comes straight across, and this BG comes straight across. And it's interesting, this looks like it has, this hydrogen peroxide has a pi bond in it, doesn't it? Crazy pi bond right there. But it also has a pi star that's populated. And so the bond order of that pi cancels with the antibonding orbital. And so we don't have this molecule can freely rotate because of that pi star being occupied. What this suggests is if you could get this in the gas phase, and I would love to do this experiment, okay? I just don't have a way to do it. If you could get hydrogen peroxide into the gas phase and ionize it to 2+, or even just 1+, that should become a double bond. It should lock into this trans arrangement, or cis, but notice how if we get rid of these two electrons, then our bond order increases, because this is sort of an antibonding arrangement. And so that would really be another confirmation of MO theory. So this is a theory, right? It makes predictions. And so with this prediction, we should be able to go to experiment now and test that. And that would be really cool if we could see that the vibrational frequency for that OO bond starts to increase because it has a tighter force constant. Or if the dihedral angle, which right now is really low frequency, 74 wave numbers for this dihedral bend, if that tightens up, because now we have these p orbitals that are side-on interacting and we don't have that antibonding orbital. So that's what I would predict, is that oxygen-oxygen bond would shrink, the vibrational frequency would go up, the vibrational frequency of the torsion would go up, and we should be able to predict this with this MO diagram. It'd be great to see if that experiment has been done, or if, we could encourage somebody, because that'd be another confirmation of the strength of MO theory.
How do you survive in gas?
Well, and that's the thing. How would you ionize it carefully enough to not destroy it? You just want to pull those last 2 electrons out. So you, again, hit it with a really, get a laser that's tunable and maybe knock those electrons out. Who knows? So here's the Gaussian pictures. They're somewhat intelligible. I've got the bottom one for sure, right? We've got this one. No problem there. The single node, no problem. This was interesting here. This AG here. You see how it seems like the p orbitals are kind of tilted a little bit because of the interaction with those s orbitals. Here's the BU orbital here. Do y'all see that? Yeah, pretty neat. And here's the it actually puts. Let's see. Yeah. So next in energy is this one's minus 25. So actually this one is next. Yeah, so that's right. This one is next. And then this one is really strange. Those gray areas, see, the white areas have kind of merged in between the molecule. So this one really only shows 2 nodes, which so there's a node there and a node there. But it actually has twisted those nodes a little bit. Yeah. And then here's the antibonding pi interaction right here. And that's the highest occupied molecular orbital, because it's the highest negative orbital in Gaussian. And so then our LUMO, our lowest unoccupied molecular orbital, is BU. And so here's the BU orbital. But see, it's kind of swapped those, hasn't it? Yeah. So it put this one higher than this one, okay, or higher than this one actually. Yeah, and then this one is the intermediate one, this AG. So it just pushed this one up to the top, and the other 2 slid down. So again, I was just drawing and trying to estimate what the ordering was, and I got it wrong a little bit. These are slightly different order at the top. So.
Other than nodes, is there any other way to estimate it?
Not really. And these nodes are crazy curvy, so it's not really easy to do. So naturally, I'm not going to take off if your nodes aren't perfect, okay? Because, mine aren't even perfect. And I'm just using p orbitals and s orbitals without twisting or turning them. And so, but did we get the correct general order? Yeah, we even got the HOMO and LUMO right. Well, not the LUMO. Let's see. The LUMO was this one. So this guy's the LUMO. But we got all, these 3 pictures correct in terms of the general idea of what orbitals are interacting. And that's really what I was looking for. Do y'all feel more confident now in terms of the symmetry adapted linear combinations and how they mix together to make the molecular orbitals?
Yeah.
Okay.
Is there any non-bonding orbital?
That's like the greatest silicone I've ever seen.
I guess this good question. This BG here is non-bonding because it's not interacting with the hydrogens, but it's bonding between the oxygens and antibonding between the oxygens. And so this idea, hopefully, let's have a little short discussion on our designations of pi, sigma, and N for non-bonding. Those are most clearly defined in diatomics, right? because in this polyatomic molecule here, let's pick this one here. Is this a sigma or a sigma star?
Depends on which sigma you're talking about.
Yeah. Right? For OO, it's sigma star.
Yeah.
For OH, sigma. But what do we mean by that sigma? Normally we say this is a sigma bond. It has 2 electrons in it, right? Well, this is a single molecular orbital. It only has 2 electrons, and it's contributing to 2 bonds, and it's harming a third. Okay, so those 2 electrons are helping out the OHs and hurting the oxygens, or not helping the oxygens. Yeah. And whereas this one, this is 2 electrons, and it's helping all 3. Okay. Yeah. This one is it pi or sigma? It's pi for the oxygens and sigma for the OHs. So you see, these designations of pi and sigma are really helpful for diatomics, but not really applicable to multiple polyatomic molecules, you know.
So there is no non-bonding orbital in here.
Not really. I mean, this comes across in terms of a non-bonding in terms of the hydrogens, but it's bonding for the oxygens. And this also is non-bonding for the hydrogens, but anti-bonding for the oxygens. Yeah. So a little bit confusing when you start adding more atoms. Makes sense, you know. And so whenever you're doing your research, say for some benzoxide, I forget the name of Dr. Gross's molecule, but you know, these diboranes and stuff, you know, and you're looking at molecular orbitals, or if you're doing things with zinc, your zinc oxide stuff, and you're looking at molecular orbitals, you can still say this orbital contributes to the strength of this bond. This orbital reduces the strength of this bond. If there's a node, it reduces the strength of the bond. If there's a lobe surrounding that bond, again, these are the areas where there's kinetic energy. So this is the oscillating of the electron cloud. And our axiom, meaning it's not provable, but our axiom is where the kinetic energy is. If we square that wave function, that's our probability distribution. So that's where the electrons are located. Okay. So that's, again, that's not been proven, but it does reproduce the data really well that we have, but there's really no way to get in there and probe that. Okay. But back up. So wherever these lobes are, that's where there's kinetic energy. Wherever there's kinetic energy, that's where the electron is. And so this is saying the electron is between the OH and between the oxygen and the hydrogen bond, or atoms. So that's strengthening that bond, because if there's electrons between 2 positive nuclei, then they're held together. And if there's not electrons between those nuclei, they're not helping. And so antibonding is really almost I wish there was another way to say it. The electrons are not doing anything to harm that bond. It's the nuclei that hate each other. And the electrons are just not getting involved. This is a domestic dispute, and the police is staying outside. The electrons are what hold the nuclei together. And so if there's no electron density between the nuclei are going to blow each other apart. So that's the anti-part of antibonding. The electrons are not getting involved. The nuclei, or the repulsion of that nuclei is allowed to separate those atoms more and weaken the bond. And that causes the bond links to increase. It causes the vibrational frequency to decrease because, again, you've got a wider potential and a weaker force constant. And so if the force constant's weaker, then the bond gets longer and the vibrational frequency drops. So,
because the oscillation takes longer for it to move.
Yeah, so if you, let's see, I thought I had, let me do presentation again. This is also some of the questions we had on one of the more recent homeworks. Let me copy that and paste it a few times. Okay, so as bond order goes up, what happens to the vibrational frequency? So let's just take an example of carbon. Well, let's do nitrogen. Okay, so each of these 5 electrons each. So we have 10 total electrons. So we go 1, 2, 3, 4, 5, 6, 7, 8. If we had 8 electrons, we'd stop there with them spin unpaired. Makes sense? You remember this? Okay. 9, 10. And so then bond order is number of electrons minus number of antibonding electrons over 2. And so we have 1, 2, 3, 4. So we have 4 minus 2 over 2. Let's see, 2, 4, 6, 8. Sorry, I can't count. I was doing, yeah. 8 minus 2 over 2, so that's 6 over 2 equals 3. So that's why we draw a triple bond, right? And again, this is most universally applicable to diatomics. That's what you get out of all of this. Bond order for hydrogen peroxide is a mystery to me, right? Because, again, how do you count it if it's a bonding or antibonding? How could you calculate bond order for a hydrogen peroxide? Right? But still, we can look to see if we've increased the number of bonds or orbitals that contribute to a bond and decreased the number of ones that have antibonding. So as bond order increases, what happens to the vibrational frequency? So bond order increases, vibrational frequency increases.
They move less, so they move a shorter distance. So it can happen.
Okay, that's one way to think of it. I think of it in terms of the force constant. So let's take it. Okay, so this vibrational frequency is equal to 1 over 2 pi c square root of k over mu. So that's the force constant. And so this is some of the homework questions. That's why I'm covering this. So this force constant is the force that's holding these atoms together. It's in newtons per meter, okay? So newtons of force, meters of distance, and so that's how many newtons it takes to stretch this bond. Make sense? So if you have a triple bond, it's harder to stretch. It's a higher force constant. If you have a double bond, it's not as difficult. If you have a single bond, it's not as difficult. So as the bond order goes up, K goes up. And it's because K goes up that the vibrational frequency goes up. Okay. And then the bond length, what do you think happens to the bond length? Yeah, let's see. So bond order goes up, the bond length gets shorter. So let's play a game. N2, and let's compare that to the vibrational frequency of N2 cation. So we're gonna play a game greater than, less than, or equal to. Okay. So we have the vibrational frequency of N2. Is that vibrational frequency predicted to be greater than or less than the vibrational frequency of N2 plus? So what happens when we take this electron out of our molecule?
Bond order changes.
Yeah.
The bond order goes down.
We've lost a bonding electron, so bond order drops, okay? And so we should see that as the bond order goes down, the vibrational frequency goes down. And so this should be this way, right? This should be a lower vibrational frequency than the triple bonded nitrogen. What's the bond order for this one? Bond order is equal to 2.5. Okay. All right, let's make another molecule now. Let's do oxygen. Let's just do this down here in the corner. O2. So we have the same sort of pattern of MO diagram. So we have 2 more electrons. You say, wait a second, oxygen is only 1 past nitrogen. Why don't we just have 1 more electron? We have 2 oxygens, so we have 2 more electrons. Okay, so that's O2. What's the bond order? So this is sigma, sigma star, sigma, pi, pi star, sigma star. So see, we put 2 electrons in the pi star, so that reduces the bond order by 1. Yeah, so it should be 2. Bond order 2. And so let's play our game again. Vibrational frequency of O2 compared to the vibrational frequency of O2 plus. Bond order for O2 is equal to 2. We take this electron out, we've lost an antibonding electron, so our bonding has gotten stronger, and so this is bond order equals 2.5. So this one has the higher bond order, so it's like this. So they're both cations, right? But again, MO theory will predict this, and it's correct. We've done these experiments. The vibrational frequency and bond order just track with each other. So bond order goes up, the vibrational frequency goes up, and down when it goes down. Yeah. So there's many different ways to confirm the molecular orbital theories, not just the XPS. We can see it in vibrational frequencies. We can see it in vibrational force constant. We can see it in the bond length.
So the bond order will be 2.5 for oxygen.
For O2 cation.
Yeah. Okay, yeah, 2.5.
Yeah. So we lost one of the. So if we did a O2, are we running out of time? Okay, O2 2 plus is isoelectronic. With N2. It's a triple bond. Yeah. Because if we get rid of both of those antibonding electrons, then it has the same MO diagram as N2. So it's isoelectronic, same electronic structure. Okay. So those were some questions that we hadn't really covered in the lecture notes that are on the homework, and I wanted to make sure that I talked to you about them. Let's see. I will give you a flow chart and the character tables just again to give you a safety net on that. That last lecture where we did the let's see. So if we have this picture, let me grab a screenshot of that. Okay, so if we have this particular, we've got BG to BU. In this picture, I've got BG and BU. Okay? is that transition allowed with X, Y, or Z polarized light? You need to know how to do this for the exam, okay? And so you set up your transition dipole moment integral with BU here, BG here. The intensity of that transition is proportional to this integral squared, okay? So if this integral is equal to 0, then it's not allowed. If it's not equal to 0, then it is allowed. And then we had Z polarized light, which was AG, right? And X and Y polarized light, which was BU. Is that correct? Okay. And so we've got time. Okay, so let's try XY polarized light. So B times B is A, and G times U is U. Okay. And so now we've sort of taken those two functions multiplied by each other. We have the symmetry of AU, and then BU. A times B is B, and U times U is G.
That's not top row.
And this is equal to 0, okay? Forbidden. By symmetry. Do y'all remember that from the lecture? Okay. This is, again, the point of symmetry. This is what we want to use symmetry for. Now let's try it with Z polarized light. So over here, intensity is proportional to this transition dipole moment integral. Okay, so AG times BG is BG. Is Z polarized light AG or AU? It's AU. I screwed that up. I'm sorry. Yeah. Plus the Z, you're not going to get. It can't be G. I'm sorry. Well, not in this molecule. Not when G's in use. Okay, so I'm sorry about that. Yeah. And so we have this AU times BG is equal to BU. This is beautiful, okay? Bring the BU down, and BU times BU is AG. And this is not equal to 0.
That's the top row of the
Character table. Okay, so you could do a HOMO to LUMO transition with my LUMO. Actually, even I think, yeah, even Gaussian's LUMO is BU. So the HOMO to LUMO transition is allowed in this molecule with Z polarized light, but not with X or Y polarized light. Okay. Vibrational motion. We don't have the vibrations in this picture, but again, doing the same kind of thing, only with vibrations. Like if I have, let me find a BU motion. Yeah, let me just draw one here. I've got a blank space. Yeah. So if I had was this asymmetric stretch BU? I think it was. And so for the transition dipole moment integral for this stretch, okay, we have BU here, but we have AG here, vibration. Because it's vibrational motion, we know the ground state's AG, the excited state, so V equals 0 for vibration is AG, V equals 1 for that motion is going to be BU. And then what we put in the middle is again Z or X and Y light here in the middle.
Is it always top row for ground state?
Yeah. Yeah, so all of the even ones. So V equals 0, V equals 2, 4, 6 are all top row. And that's it. That's one of the lecture notes. I'm just highlighting a few of the lecture slides that I want to quiz you on in the exam. And so this is definitely one of those too. Let's go back and find that one. It's sort of a summary slide. And I say electronic spectroscopy is not like vibration and rotation. And I have vibration and rotation have the top row in there. But as electronic, you have to know
This one level.
yeah, you need to know this right here and this right here. Neither one of those is top row. Okay. But in vibration and rotation, one of those, in these three pieces here, one of these is top row. Okay, just because that's a nuance that people may forget and you'll get that wrong. I don't want you to get it wrong. I want you to remember vibration and rotation have top row as one of those pieces, and then the vibrational motion or the rotational motion is the other piece, and then light is always in the middle. And you find light in that character table by going up here and finding here. So you have light here, Z, and XY. And so since vibration, one of those is top row, if I have a BU mode and I see X and Y here, I know that's infrared active. If I'm up here in BG, let's say I have a BG motion, a vibration that's BG, I know it's not infrared active because it's not on either one of those, but it is Raman active. Okay, all of these double, order ones are Raman. So if you have a vibrational motion that's a G, it's going to be Raman active. If you have a vibrational motion that's U, it's IR active. And because you have G's and U's, you have the rule of mutual exclusion. You can't have a vibration that's both.
IR is flow source of one axis.
Yes, X, Y, or Z. And Raman are all the double ones. X squared or XY or YZ. Yeah. And notice this is Y times X. This is X comma Y. Okay, so this is X by itself, Y by itself. And up there it's X times Y. Okay. I think that's enough. We're 2 minutes over, so